In this video, I'm going to work an absolute extreme problem for a function involving the natural exponential function. So we are asked to find the absolute maximum and minimum values of the function f of x equals x times e to the 1 over x squared when the domain is restricted to the closed interval between 3/4 and 3. Okay, so looking at this, let's be sure that it's clear what this function actually means. Up in the exponent, there's a fraction. The x squared in the denominator happens first. That's the most deeply nested operation here. Then we have division, then the natural exponential operation, and then finally we have multiplication. So, a couple of things to think about. We need to take the derivative, but what rule should we start with? The product rule, because multiplication right there is the outermost operation in this formula. We will eventually need the exponential rule and the chain rule, but we need the product rule to start with. Okay, let's work on that. So for the left, that's x, and the right is e to the 1 over x squared. The derivative of the left is very easy. What is it? 1. For the derivative of the right, I'm going to suggest that we do some algebra first and rewrite it as e and then put x to the negative 2 up here. What I've done there is just look at the 1 over x squared subexpression and remember that in general 1 over a to the n can be rewritten as a to the minus n. The reason for doing that is that it will save us from having to do the quotient rule in a moment. Now we're ready to take the derivative of the right. The outermost operation is the natural exponential, so we will start with the exponential rule. And remember that the derivative of e to stuff is e to stuff. So e to the x to the minus 2. So that's the exponential rule. But then we have to include the chain rule factor derivative with respect to x of x to the minus 2. Next step, we'll keep the part that we're finished with, and then the derivative with respect to x of x to the minus 2, negative 2, x to the minus 3. And if you like, you can clean that up a little bit. It's just normal to put stuff like the 2 times and the x to the negative 3 times to the left of the exponential part. Now we've got both parts of the original function. We have the left, we have its derivative, we have the right, and then way down here we have its derivative. Now it's time to use the product rule to put them all back together. Okay, f prime of x equals. Remember the product rule has two parts. Copy of the left times the derivative, sorry, I said that wrong. Derivative of the left times a copy of the right. I'm actually going to use that form for the copy of the right just to keep things consistent. So 1 times e to the x to the negative 2 plus the other half of the product rule is copy of the left times the derivative of the right. This is going to be a really floppy x, but there it is. So x times negative 2x to the negative third times e to the x to the negative 2. So that is the derivative. Since we want to solve for critical numbers, we should simplify this. A couple of simplifications. We don't really need times 1. Also, over here, you can see it's several things multiplied. So that's multiplied, that's multiplied, that's multiplied, that's multiplied. So we don't really need these parentheses. Now I can imagine grouping the multiplication by x with the multiplication by x to the negative third. Okay, so first step, let me just copy the part that was easy to simplify. Then over here, I'm going to copy the factor of negative 2. X times x to the negative 3 simplifies to x to what power? X to the negative 2. Then times e to the power x to the negative 2. Finally, mostly the next line I can just rewrite this a little more smoothly. Since I have a negative factor in this group of 3 factors, I can replace that addition with subtraction. And now I have 2 times x to the negative 2 times e to the x to the negative 2. So that's as good a place as any to stop with the derivative. Now remember where we're going with this. We're looking for absolute maximum and minimum values for a smooth function on a domain that's a closed interval. There are only a few candidates for the absolute maximum and minimum, and they are the left and right endpoints and any critical numbers. We've taken the derivative of f, so we're on our way to finding critical numbers. So to find critical numbers, what do? We set f prime equal to 0 and solve. Okay, e to x to the negative 2 minus 2 times, oops, forgot this part, x to the negative 2 times e to the x to the negative 2 equals 0. Initially, this looks kind of scary. We've got e's all over the place. There's 3 places where there are x's. There are negative exponents and everything. But don't panic. Turns out that this is relatively easy to solve. The first step is to factor it. Now, how do you know to factor it? When you do the derivative of a function that has an exponential subexpression, since that will generate copies of that same exponential subexpression, there's a pretty good chance that you'll be able to factor out the exponential subexpression. That's this e to the x to the minus 2. So e to x to the minus 2 times, okay? To handle that term, I need to put a 1, then the subtraction, and then finally, over here, I need 2 times x to the minus 2. Again, to check this, if you were to distribute this out, it should return to that form. Remember how solving a factored equation equal to 0 works. The solutions to factor times factor times factor equals 0 are the solutions to first factor equals 0, solutions to second factor equals 0, solutions to next factor equals 0, and so on. So let's try e to the x to the minus 2 equals 0. Now at this point, I need to remind you of something about the exponential function. There's two ways to see this. So the one way is that e to a number is always positive. Never 0, never negative. That means that there is no number you can stick up here to get e to that number equals 0. That means that there is no number you can stick up here in for x that will give a solution to e to the x to the minus 2 equals 0. So that's the first way that you would know that this has no solution. The second way is that you could try applying ln to both sides. Very often when we've tried to solve equations that have an e to the unknown somewhere in it, we're able to use the natural logarithm. That would give us just the stuff up in the exponent here, x to the minus 2, and we would still have this ln of 0 on the other side. But here's the thing to remember. The domain of ln is only positive numbers. If you try to do ln of 0 in your calculator, it will give you an error message because there is no way to define ln of 0. So however you want to see this, the key point is that e to the x to the minus 2 equals 0 has no solutions. So that means we don't need to worry about that factor. So no solutions here. But it's possible that we might have solutions here. So let's try that. So let's try 1 minus 2x to the negative 2 equals 0. This equation only has the unknown x in one little place. So we ought to be able to peel the onion and solve for x. Okay, first operation we need to undo is this 1, which is effectively added in. So let's subtract 1. That leaves negative 2x to the negative 2 equals negative 1. Now we should divide by negative 2. That will leave us with x to the negative 2 equals, and here I can, let me stick to this brighter color. I can do a double negative simplification and be left with 1/2. Dealing with an equation x to the negative 2 equals 1/2, that may seem a little bit strange. I'm going to suggest that there's two ways to think about it. One way is to first replace x to the negative 2 with a fraction and use fraction notation instead of the negative exponent. That would give what? So that's 1 over x squared. And just to remind you of that, we actually did the reverse. Where did it go? We did the reverse up here because it made the derivative easier to work out. Okay, so back to solving this. We have 1 over x squared equals 1/2. Now you can take the reciprocal of both sides. That means just flip the fractions over. That takes us to x squared over 1 equals 2 over 1. We really don't need denominators of 1. We can just remove those, and that leaves us with x squared equals 2. This is starting to look much more promising. What are the solutions to x squared equals 2? Well, x equals plus or minus the square root of 2. Remember that only numbers in the domain are relevant as critical numbers. The square root of 2 is about 1.4, but our domain is from 3/4 to 3. So let me write that down. The domain is from 3/4 is 0.75 to 3. Square root of 2 is approximately 1.414. So is square root of 2 in the domain? Yes. This is in the domain. What about negative square root of 2? Nope, it's not in the domain. So there's only one critical number that we need to deal with. Okay. Let's check our candidates. So for the left, we need f of 0.75. There's a critical number, f of square root of 2, and then there's the right endpoint of the domain, which is 3. Well, let's go over to the calculator and see what happens. Okay, let me quit out of that and clear that out. I'm going to go, since we have to plug in 3 different numbers, I'm going to go to the y equals screen. Let me clear out that problem. The function that we are interested in is x times e to, let me put in a fraction template, 1 over x squared. Okay. Table is set up in ask mode. There's table. Let me delete out stuff from last time. The numbers we need to put in are 0.75, square root of 2, and 3. Okay, so the numbers that we've got are f of 0.75 is 4.4375, f of square root 2 is 2.3316, and f of 3 is 3.3526. Okay. So which of these y coordinates is the greatest? That's this one. So this is the absolute maximum. Okay, which of these y coordinates is the least? 2.3316. So that is the minimum. So here we go. The absolute maximum value of f is, and I'll write this as f of 0.75, approximately equal to 4.4375, and the absolute minimum value of f is f of square root 2, which is approximately 2.3316. If we wanted to, we could check this using the calculator. I'm going to go to the plot window screen. I'm going to use xmin equal to the left boundary of the domain, which is 0.75. I'm going to let xmax be the right boundary of the domain, that's 3, and an x scale of 0.1 seems reasonable. For ymin, I want to be able to see this 2.3316. So how about I'll set ymin to 2, and we need to be able to see 4.4375. Let me set ymax to 5. And y scale of 0.1 seems reasonable there. Let's call up the graph. Okay, there you go. There's the absolute maximum. If I type, I have to hit trace, don't I? Trace, and now let me type square root of 2. That takes me to that. That looks like it is indeed the absolute minimum. And then this point was one we still had to check, but it came out in between. So there you go, absolute maximum, absolute minimum.